All right, so we're happy to have Chintan Patel, TIFR, and also visiting KIT now. Tell us about endpoints of charge superradiant facilities in AdS5 system.
Thank you for inviting me here. So today I'll be talking about this paper that came out last month. It's on endpoint of charge superradiant instabilities in AdS5 cross S5 black holes. This is with Sunjin, Diksha, Seok, Vidit, Umbu, and Shiraz. So these are the contents that I will be going through in my talk. First, I'll give some basic introduction of charge superradiance in AdS black holes. Then I talk about the solutions called hairy black hole solutions, which were proposed in the past as endpoints of the superradiant instability. Then I talk a little bit about what role the dual giant gravitons will play in our story. And then I'll make a proposal for what we think is the correct endpoint of charge superradiant instability. And I'll also give a description of what the supergravity solution that we are proposing. And then some future directions. Okay, so it's been known since quite some time now that there are a certain class of black holes in AdS which are unstable to emission of charged particles. So Globsar had first considered a minimally coupled scalar field in the background of a Eisen-Nostrom black hole and investigated its dynamics. So what you observed is that you can have a scalar field which has when you tune the scalar field's charge to some critical value, it can have a static profile in the black hole background. And when the charge of the scalar field exceeds this critical value, the scalar field becomes unstable in the background of the black hole. In other words, if you fix the charge of the scalar field and keep on increasing the chemical potential or the charge of the black hole, you see that the scalar field becomes unstable. Now there is a very simple thermodynamic reasoning for this instability. So consider a small charged black hole in AdS which has some chemical potential mu and inverse temperature beta. Now suppose that initially you just have a black hole, and in the second configuration you emit some mode, scalar field mode which has energy delta E and charge delta Q. Now you can compute the change in entropy of the black hole when this mode is emitted. And the change in entropy of the black hole will basically be this. It will be proportional to delta E minus mu delta. Now the reason I wanted to consider small charged black hole is that the energy, if the black hole size is small, then the energy of this mode can be approximated as the energy in pure AdS. It will be corrected as per the charge of the black hole. Now for modes in AdS5, the charge of the mode is bounded from above by its energy. So the energy charge has to be less than its energy in pure AdS. This is true in pure AdS, but it can get corrected in the black hole background. Therefore notice that if mu is greater than 1, okay, if mu is less than 1, then the right hand side is always negative. That means that whenever you increase such a mode, you cannot increase the entropy of the black hole. So black hole is stable entropically against emission of this mode. However, when mu is greater than 1, you can emit such mode which has, let's say, delta E is equal to delta Q, something which saturates the bound, and then you can increase the entropy of the black hole. So this is like a second law of thermodynamics. The system wants to increase the entropy by emitting such modes when mu is greater than 1. Okay. There is also a Lorentzian way of understanding this instability using quasi-normal modes of the scalar. Now, I think most of you might be familiar with quasi-normals, but basically a quasi-normal mode is the frequency at which any perturbation outside the black hole oscillates with. So in the black hole background, usually the modes go like e to the I omega t, and this omega can be complex. So this is just saying that if omega has real positive imaginary part, the amplitude of the mode decreases with time. However, in this paper, they considered some small black hole and they coupled some scalar field to it. And what they observed is that when the chemical potential of the black hole exceeds this critical value, the sign of the imaginary part of the quasi-normal frequency changes. So this is also suggesting that the mode, when perturbed from outside, increases in amplitude with time. So it's suggesting an instability. Okay. Now this critical value actually is 1 in the limit of small black holes, but actually gets corrected, and it's always greater than 1. The critical value at which the mode becomes unstable is greater than 1. Okay. So now let me just show the phase space of charged black holes in AdS. So this is fixed energy versus charge. The colors are not. This is green curve, and the green curve is the bound which is E is equal to Q. This is the unitarity bound from the boundary CFT. The blue curve is the extremality curve, so there are no black holes below the blue curve. And the orange curve is mu equals to 1 curve. So in most of the cases, the instability actually kicks in below mu equals to 1 curve. So imagine that this is mu equals to 1, and this is the instability curve, this is the extremality curve. Okay. However, mu equals to 1 curve will play an important role in our story. So all the black holes which are below this critical curve are unstable, and one might ask that from boundary CFT point of view, what's the correct entropy of the states corresponding to these charges? Because if the black holes are unstable, then clearly there is a configuration with greater entropy. So they are not capturing the correct entropy at fixed charges. Are there any questions?
Are we still discussing small AdS black holes or not?
Actually, people have extended the story to large AdS black holes where you can do numerical analysis to find this critical value and so on. So the small black hole I mentioned just for the sake of simplicity, because then mu, the critical value roughly becomes 1. But it turns out that for even large black hole, the critical value is always greater than 1. And I'm emphasizing this point because there are the 3 branes which will become unstable when mu is equal to 1. So all this critical value is actually above the instability point for the 3 branes. So that's why I'm emphasizing the mu equals to 1. Okay, so yeah, so as I said, the natural question might be what's the endpoint of this charge superradiant instability. Now in the past, the endpoints of these superradiant instabilities are suggested to be the solutions which are called hairy black holes. Now these are solutions which have a sea of scalar field condensate surrounding the black hole, and it's a static profile. So there is a scalar field which carries very large amount of charge and energy, and then you have a central black hole. And the black hole has critical chemical potential, so the full configuration is stable. Okay. And in the microcanonical ensemble, you basically replace the pure black hole solutions with these solutions, and these solutions actually exist all the way to unitarity bound. So all this region is completely filled by these hairy black hole solutions. And notice that previously there were no solutions between the extremality and the unitarity bound. Okay. Now all these works that I mentioned, they considered some toy models where you have some global AdS space with some single charge scalar field. Okay. However, most holographic models that we know of have some internal manifold, so they are of the form AdS m times mn. In this work, I will be basically talking about type 2b supergravity in AdS 5 times S5. So the R symmetry of the Dual field theory is SO6, which is the rotations in S5, and as there are 3 cardinal charges Q1, Q2, Q3. Now when we do dimensional reduction on S5, there is a huge tower of charge scalar fields, which on the boundary theory are the single trace operators of this form. Okay, so we don't have one scalar field, but we have an infinite number of scalar fields. Okay, and at first it seems like it might be a very difficult task to analyze such a system where you have a lot of scalar fields and so on. However, classically there is a consistent truncation of type 2b supergravity, where you can basically turn off all the scalar fields which have more than 2 x's classically. So in classical equation of motion, they always appear more than linearly, so you can consistently turn them off. Okay. In a further, again, these are like 21 scalars, but in a further truncation, you can basically truncate to just one scalar field whose dimension and charge both are 2. And notice that the way they couple to gravity and to gauge field is not minimal, it has some complicated coupling. Now for this system, so we are working in AdS5 times S5 black holes with this single scalar field turned on. The hairy black hole solutions were constructed which have C of this particular scalar field. Okay. Now again I am emphasizing that all these solutions, all these hairy black hole solutions had some critical value where they become stable and it was always greater than 1. Now the question one might ask is that the above solutions seem like they are stable in classical configuration because the other fields are just turned off. But it is always possible that quantum mechanically the other modes can get turned on, right? And they can become unstable. Now we claim that the hairy black hole solutions constructed are in fact unstable to a tower of very high charge scalar fields. And they all lie outside the consistent. In fact, the instability, as I will show, exceed at critical value which is 1 rather than the critical value greater than 1 where the single scalar field got unstable. And we propose an endpoint to this instability which has higher entropy than the hairy black hole solutions, and these solutions lie outside this consistent truncation. So I will show that the expectation value of all the higher charge scalar fields is non-zero in this background.
So it seemed even before the quasi-normal modes develop a zero.
Yeah, so even before the quasi-normal modes of that scalar field, the race x square scalar field quasi-normal became zero. Yes.
Sorry, do the hairy black holes described here break the SO6 R symmetry?
The hairy black holes?
Do they break the SO6 R
Yes,
symmetry?
they do break the SO6 R symmetry because they are charged under the SO6 R symmetry.
And these endpoints also break the R symmetry?
They do break the R symmetry. Yes. Okay. So we will see that any black hole with chemical potential greater than 1 will be unstable to emission of dual giant gravitons with very large charge, and I'll explain what this means. What we propose is that the endpoint of this instability is what we call dual rest black holes. These are solutions which consist of a very large dual giant graviton surrounding a mu equals to 1 black hole. Okay? And we also construct supergravity solution by taking the back reaction of these dual giant gravitons into account. And as we will see, these solutions have non-zero expectation value of all the higher charge scalar fields. So this is the final result, and then basically now I'll be talking about some technicalities. So I'll take a small detour to just give a basic introduction to dual giant gravitons. So dual giant gravitons are D3 planes which wrap an S3 in AdS5. So they are at some particular radial distance in AdS5, and they are point-like particles on S5 and they move along some great circle on S5. So just to draw in pictures, imagine you have this AdS space and they wrap some S3 in AdS space, so they are at some fixed distance r, and on S5 they are point-like particles and they are rotating with some velocity along some equator. Okay, and hence they carry some charge under the SO6. Now one dual giant graviton, since it's a D3 plane, is also charged under the 5 form field strength. It carries unit charge in some conventions under the 5 form field strength. Okay. Now the motion of dual giant graviton in S5 causes it to expand into orthogonal radius space. This is the Myers effect if people are familiar with it. People might also have heard about the usual giant gravitons. So giant gravitons are very similar, but they rotate on an equator in S5 and they wrap some S3 on S5 and not in AdS5. So they are point-like particles in AdS5, just to differentiate. Okay. So first now we'll consider dynamics of the dual giant gravitons in pure AdS space, and then we'll go to black hole right now. So first let us consider dual giants in pure AdS. Suppose I use these coordinates r, t and s, any three coordinates on S3. And on S5 I use 3 complex coordinates z1, z2, z3 such that sum of their magnitude square to sum of their square of magnitudes is 1. Now the action that dual giant gravitons take is as follows. So this n is the tension of the D3 brane. The first term is the first term is basically square root of h, where h is the induced metric on the volume of the dual giant graviton. And the second term c is the coupling of the four-form field strength with the dual giant graviton. So this integral is over the volume coordinates on the D3 brane. Okay. Now let us consider dual giant graviton sitting at some radial distance r in AdS, and it's at z2 equals to z3 equals to 0 and rotating on a great circle, on one great circle in z1 plane, let's say. Now with all the other, so we turn on all the other velocities to 0 and we basically just have non-zero velocity along the z1 plane. Now we can find the stable minima for this. It turns out that the stable minima that this dual giant has is at radial distance r in AdS, which is related to its momentum along S5 by this relation. So basically, the radial distance is the square root of the momentum written in units of capital N. Okay. In fact, we can plot the effective potential for dual giant gravitons. So this is the effective potential as function of the radial distance in AdS5 for fixed charge. So this orange curve is when I keep the charge to 20, let's say. So you can see that there is a minima at square root 20. This is written in units of n. And the energy at this minima is also 20. So the energy and momentum are equal, so it's a BPS configuration. Similarly, here I have momentum which is 10 and energy is also 10. And it sits at radial distance which is square root 10. So this will be important to remember that whenever it has large momentum, the radial distance is also very large. So as I increase the momentum of the D3 brane, it will sit at a larger radial distance. Is there any question up to this? Okay. So now we can do similar analysis where we put this dual giant graviton in the black hole background. So we will work for simplicity with black holes which has all the three equal charges. So this configuration breaks, so as you mentioned, it breaks the SO6 symmetry down to a U3 subgroup. Okay. So now the dual giant gravitons will have charge under this U3. Now a general charge matrix which will be an adjoint of U3, so it will be a 9x9 matrix, and the general charge matrix will be U3 equivalent to a diagonal matrix with two unequal charges. Okay, this one can easily show. It turns out that the dual giant gravitons which will be important are the ones which has only one non-zero eigenvalue. Okay, so again we can do the similar thing. We can write an action of the dual giant graviton in the black hole background. Now here I am considering black holes which preserve some of the rotational symmetries in S5. In AdS5, and therefore I can basically in the volume coordinates I can integrate out the S3 directions of the D3 brane, and therefore I am left with a action for a particle in the orthogonal 7-dimensional space whose metric takes this form. So this is a one line of a particle coupled to a gauge field. This comes from the four-form potential. The second term is the coupling to four-form potential. The first term is the induced metric. And the 7-dimensional metric takes this form. So this T, R, and CP2 and psi are the coordinates which are orthogonal to one volume of the D3 brane. This CP, the CP2 is basically indicating the U3 that is preserved by the background, because CP2 preserves U3. And the last two terms are basically coming from S5, because S5 can be viewed as a U1 fibration over CP2. So this psi is the fiber direction. Okay, so now we do the same thing. We fix the charges Q1 and Q2. Remember that Q1 and Q2 were the diagonal charges of the U3 matrix. And we can write an effective potential for this particle in terms of Q1 and Q2. Okay. Now once we choose this form of the charge matrix, Q1 and Q2 are basically rotations in Z1, Z2 plane. So only non-zero velocities are phi1 and phi1 dot and phi2 dot, and all the other velocities will become zero. And the Hamiltonian for fixed Q1, Q2 takes this simple form. First term is coupling to the background gauge field. This is the gauge field corresponding to the R-symmetry charge Q. The second term is the usual kinetic term for a relativistic particle. It's of the form square root p square plus m square. First term is like p square, and second, this r to the 6 is like m square, because the mass of the dual giant is proportional to its size r, which goes like r cube. And the second term, and this term is coupling to the 4-form potential. Okay. Now to find stationary solutions, we simply put qr to 0, we move the radial momentum to 0, and we again find the effective potential for fixed charges, and I'll show the plots for them. So now first, when I fix mu to be less than 1 over cos 2 gamma, this gamma was the parameter in charge matrix, so I wrote this charge matrix q1, q2 in terms of two parameters q and gamma. So when I choose the chemical potential of the black hole to be less than 1 over cos 2 gamma, it always has this kind of feature. So what? So now you see that there is a minima which is outside the horizon. So this value, where it begins, is the radial distance. This r is the radius of the horizon. So you can see that the energy value at minima is always above the effective potential at the horizon, when mu is less than 1 over cos 2 gamma. When I increase mu, so when I take mu which is greater than 1 over cos 2 gamma, then something funny happens. Now the minima is below the value of the effective potential at the horizon. So what this is suggesting is that when mu is less than 1 over cos 2 gamma, if I put a D3 brane here, it will like to tunnel inside the black hole. However, if I choose mu greater than 1 over cos 2 gamma, a D3 brane has a tendency to go to be emitted from the black hole and sit near this horizon, near this minimum. Okay. In fact, the minimum value where this instability starts is when gamma is 0. So when mu is and when gamma is 0, the charge matrix only has one non-zero eigenvalue. So this is suggesting that as you cross mu equals to 1, the D3 branes with just one non-zero eigenvalue want to tunnel out from the black hole. Okay. Are there any questions up to this point?
Maybe you will comment on this later, but branes located in external fields, they themselves sometimes unstable. They turn into other branes. Is it also the case for these D3 branes, or they are stable if you're studying them in the background of a black hole or some electrical charge?
Yeah, so in fact, like these branes are, in the effective potential, we are taking the electric field from the black hole into account. So the effective potential has everything into account. And what I'll show is that if the chemical potential is exactly 1, you can actually put some D3 brane and it will be stable at that point.
Yeah. So this is just the potential for the location of the brain. I'm asking about if the brain itself is stable, or maybe it wants to decay into like something else.
For example, like.
Yeah, I think there are examples when you have a fundamental. I think if you have D1 brain in the electric field, it wants to become a composite of D1 and also like the fundamental stream.
I see. Okay, here I have a D3 brain.
No, I mean,
Yeah, I'm not sure if there is any instability of the kind that you are talking about. But yeah, if you have something in mind. Okay. Yeah, so as I said, the above discussion is suggesting that the dual giant gravitons want to be emitted from the black hole if the chemical potential is greater than 1, and they'll be absorbed by the black holes if chemical potential is less than 1. Now this paper in 2006 already had such an indication from boundary theory point of view. So they found the partition function. They are trying to find the free energy of the n equals to 4 superorbitals at weak coupling, and they found that when mu crosses 1, like when mu shifts from less than 1 to greater than 1, there is a mode which has negative effective mass. So there is so that was an indication about such an instability from boundary. Now the above analysis was purely classical, but we can also do quantum mechanical analysis by quantizing the orbits of the dual giant graviton in black hole background and confirm that this tunneling tendency is correct. Okay, so basically what we do.
Sorry, so this recoupling analysis, so initially you had the potential which was like going to like very negative value, right, at the horizon.
Here?
Yeah.
Yeah, here I am choosing the value of the potential to always be 0 at the horizon.
So it kind of, no, it rises. Yes. Sorry, please go ahead. I realize that this question I'm going to ask it doesn't exist.
Okay. Yeah, so basically like what I will now talk about is to quantize this orbits of the dual giant graviton. And what we will do is that we will write fictitious, like we will take a fictitious scalar field whose quantization gives the dual giant gravitons. This scalar field will sit in this fictitious 7-dimensional metric that I talked about, the metric which was like orthogonal to the D3 brane, and it's coupled to a four-form potential which is C. Okay. Now there is an overall n factor multiplying the action which is coming from the tension of the D3 brane, and it suggests that we can use the semi-classical WKB approximation to find the quasi-normal modes. And basically we'll use the same intuition that if there is a change in the imaginary part of quasi-normal mode, then there is an instability towards emission of these objects. So basically we want to solve this equation for the scalar field where G tilde is the metric, 7-dimensional metric, and the covariant derivative has a coupling to the 4-form potential. Here it just becomes a gauge field because I am just considering point-like particle. I integrated out the S3 directions. So as we usually do, we pick some ansatz for the field, for the scalar field, and we want to solve for this function g of r, and we have to put the appropriate boundary conditions that we usually put for quasi-normal modes. So by choosing this form, I basically convert my Poisson's equation to a Schrodinger type equation, and I have some effective potential. And notice that I have 1 over n square here, so 1 over n basically acts like a effective h bar. So I can use the WKB approximation. The schematic potential will be shown next. And for quasi-normal modes, we have to impose the boundary conditions that the field is ingoing at the horizon, and it's not outgoing. It should be like normalizable at infinity. In AdS, these are the boundary conditions that we have to put. And this means that this g of r near the horizon should go like e to the minus I omega rs, where rs is the tortoise coordinate. Okay, this is the plot of the effective potential which appears in this equation. And we just use the usual WKB approximation to find the tunneling, to basically find this omega here, which satisfies the correct boundary condition after solving the equation. Okay. So we find omega of this form. So omega has some real part and some imaginary part. The real part basically is the energy of the D3 brane, which we find classically. This is what we get in the usual WKB approximation. Now the interesting thing is the imaginary part. So notice that imaginary part has sine hyperbolic of cos 2 gamma inverse minus mu. So it's the same point like when mu crosses 1 over cos 2 gamma, the imaginary part changes the sign, and hence it's confirming the classical intuition that we previously saw. And notice that this tunneling, this imaginary part is extremely small, it's exponentially small in n. And this is also what we usually see in the WKB approximation, that the tunneling probabilities are exponentially small in 1 over h bar. Okay, so we clearly see that there is this instability from quasi-normal modes, and the first instability kicks in when gamma is 0. Okay, now what we propose is that when you have a black hole which has mu greater than 1, then the true endpoint, so let me just show in figures. So suppose now you are at this point, you have some black hole which has mu greater than 1, this red curve is mu equals to 1. Now you want to ask what is the correct entropy for solutions at this point. So you basically just draw 45-degree lines from here and you go to the red curve. And your solution it consists of a black hole on the red curve, which is surrounded by a dual giant graviton with the remaining charge and energy. And since the charge is of very large scale, like the charge is of some order n square, this dual giant graviton will be at radial distance which scales like square root n. So this dual giant is actually very large and it carries a very large amount of charge and energy. And one more thing is that since I have 3 unequal charges, I will need 3 dual giant gravitons rather than 1 dual giant graviton. Okay. So this is the proposal for endpoint of the charge superradiant instability. For any point here, the correct solution is to go to draw 45-degree line, and you have a black hole here, and the remaining charge and energy are in the dual giant graviton. And since the dual giant graviton is very large, it's sort of a non-interacting mix between the black hole and the dual giant. So they interact very weakly. Okay. And we can compare the entropy of these solutions with the hairy black hole solutions, and it turns out that the hairy black hole solutions have less entropy than these solutions. I won't go much into detail on that. Okay, and this we can also extend. So previously I just talked about non-zero angular momentum of the black holes, but we can also extend to situations where we have, previously we had 0 angular momentum in the black hole, but we can extend to situations which has non-zero angular momentum in the black hole. So we have SU2 left and SU2 right as the rotational symmetry in AdS5. But still I am putting one of the angular momenta to 0 because this simplifies the analysis. And I have the other angular momentum is non-zero. So in this situation, again, this red curve is the instability curve, mu equals to 1. So all the solutions below this are replaced by the dual giants. Any questions? Yeah. So now you might ask that why only one dual giant graviton? Like you could have emitted more dual giant gravitons. And the answer is again entropic. So the entropy of any black hole takes this form. So it's of the form n square times some function of energy and charge written in units of n square. Okay. Now when you emit k dual giant gravitons, the phi form flux also reduces by k units. So here this n is the phi form flux near the black hole. So when you emit more and more dual giant gravitons, there is reduction in this factor. The n square decreases, but these two factors increase because n square is in the denominator. How much n square?
Okay. At least 25.
Okay. Yeah. So basically, there is a competition between two terms. There is decrease in entropy if I emit more dual giants because the phi form field strength is decreasing, but there is increase in entropy because of this term. However, it's easy to check that on the red curve, the mu equals to 1 curve, emitting more dual giant gravitons always decreases the entropy. Okay, and hence the maximum entropy situation is when you have as less number of dual giant gravitons as possible. So for three non-zero charges, I will have 3 dual giant gravitons in the final configuration. Okay. Yeah, and this is basically the phase diagram when we have non-equal charges. So it's not very clearly visible and it's not very important, so I'll just take it. Yeah, that's fine. So basically what happens is that when you have all 3 charges in the black hole which are unequal, let's say you begin with very high values of energy, the black holes are all stable. As you keep on decreasing energy, you hit a line where one of the chemical potentials become 1. So basically you emit dual giant gravitons which rotate in the direction of along with the chemical potential became 1. As you further decrease the energy, one more chemical potential become 1. So now you need 2 dual giant gravitons. And as you further decrease the energy, 3 chemical potentials become greater than 1. So you need 3 dual giant gravitons. And then similarly, you can have situations where you have 2 unequal charges and so on. Okay. So now till now we just considered dual giants in probe limit. So where we didn't take the back reaction of dual giants into account. However, since the dual giant is very large and it's very far from the black hole, we can actually very simply find the back reaction of the dual giant graviton. In fact, we can treat the dual giant gravitons as if they are almost in AdS space and then find their back reaction, and then there will be further corrections which are suppressed in 1 over n. Luckily, the supergravity solutions which describe the presence of a single dual giant graviton in pure AdS5 times S5 have already been studied in this famous paper by Lin, Lunil and Mardasena. So we basically just use the supergravity solution that they have and we add to the black hole solution. Okay, now these are half BPS solutions in type 2P supergravity. Now, if for people who are familiar with the solutions, these solutions are basically described by some boundary conditions on a 2-dimensional plane. So the boundary conditions which are as in the first picture correspond to pure AdS space. In the second picture, if you take basically the area of this black block corresponds to the total 5-ohm flux. When you take some chunk of this black dot somewhere far, this corresponds to a dual giant graviton. A hole in the middle corresponds to a giant graviton, and if you have some fluctuations on this, they correspond to like the usual gravitons in supergravity. Okay. Now, from boundary theory point of view, this dual giant graviton corresponds to some excitations of the eigenvalues of the matrix X that I was talking about. Okay. So now we can just take the back reaction that we get from LLM paper, and we can see that this is the 5-ohm field strength and this is the metric perturbation that this D3 brane has. And we can see that it has the correct singularities that the D3 brane should have. Okay. And in fact, we can also go to distances which are order unity in AdS. So suppose the D3 brane is very large. And we can check that the metric and field strength both fall off as 1 over r to the 4, where r is the distance from r is the size of the D3 brane. And because the strength of the back reaction from one brane is also order 1 over n, we can see that the effect of brane near the black hole is subleading, it's order 1 over n. Because of this, we can simply add in the total metric, we can simply add the black hole metric and the LLM metric and the subleading corrections which will be 1 over n cube, and this can be perturbatively accounted for. They are just linear combination because of the non-interacting mix. Okay, this I already said. And we can also do one thing. We know the 5-ohm field strength which is sourced by this D3 brane, and by doing the Fourier decomposition of this 5-ohm field strength into spherical harmonics of S5, we can find the expectation value of higher trace operators. These are the higher charge fields, and we can explicitly find their formula. Okay. So this is basically suggesting a phase transition from boundary theory point of view. That when we are at some point here, all these higher trace fields are 0. The expectation value are 0. But as soon as we cross this mu equals to 1 curve, they get turned on. So this is a signal of phase transition from the boundary theory point of view in microcanonical answer. Okay, so that was basically my talk. So to summarize, we have a conjecture for endpoint of charge superradiance instability in rotating black holes in AdS5 times S5. The endpoint solutions are mu equals to 1 black hole surrounded by a dual giant with very large radius. We also give a lower bound on the entropy in charge space which extends, so these solutions basically extend all the way up to unitarity bound. And we have prediction for new phase in n equals to 4 superambits, which corresponds to turning non-zero expectation value of higher charge operators at large charges and energies. And we also have a perturbative supergravity solutions which describe this phase. Now some of the possible future directions will be to understand this phase from the boundary theory point of view. One can hope to find some exact supergravity regime where there are no singularities. So if you have some order n d branes, then it will be a smooth solution. Even though it will be unstable, but still one can hope to find some smooth solution where you have a lot of divergent gravitons. Then we also consider a simple situation where Jr was non-zero. So if both the angular momenta are non-zero, then the situation becomes a bit more complicated. We can also extend this situation to supersymmetric solutions. So we can have a supersymmetric black hole which is surrounded by a d3 brane. And in fact, we have checked that the d3 brane configuration in the background of supersymmetric black hole is exactly supersymmetric at the probe level. So we can do the kappa symmetry analysis and check that we can have supersymmetric d3 brane configurations around the known Butowski real black holes. And this is suggesting that we can extend the known supersymmetric supergravity solutions to, I don't know if people are familiar, but suppose I try to find supersymmetric solutions in n equals to 4 superambits, and I have two charges, let's say Q and J. I could have supersymmetric solutions everywhere, but the black holes are only known to exist on a one-dimensional curve. So the supersymmetric solutions away from this one-dimensional curve are not known. But now this is suggesting that I can take a supersymmetric black hole and rest it with some dual giant graviton. So I give this much charge to dual giant graviton, and I can find new supersymmetric solutions which extend this one-dimensional curve to like higher dimension. And then we also have some implications on the superconformal index. This work we have not yet published. But basically what we are observing is that superconformal index is something which is protected from the boundary theory point of view. And it has been known since 2018 or something that the entropy of the supersymmetric black holes is reproduced by the saddles in the superconformal index. But since now we have solutions which extend in the full two-dimensional plane in the charge space, it turns out that there are some charge configurations where these solutions dominate over the black hole solutions. So this is something which we will put in a month or something. So yeah, I think that's all.
Questions for Chintan?
Sorry if I missed this, but presumably when you have this evaporation and giant gravitons, your entropy must go up.
Yes.
It means that this gas of giant gravitons must have very high temperature.
So that I mentioned. Actually, the configuration which has maximum entropy for black hole only has one dual giant graviton, or as minimum possible dual giant gravitons as possible.
Could you say this again?
Yeah. So you could imagine that you have a configuration where you have a black hole and that it emitted one dual giant graviton. But you could look for a similar configuration with same charges, but now the black hole has emitted more dual giant gravitons. But it turns out that configuration has less entropy. Why? Because so the entropy of black hole is of this form: n square times some function of q by n square and e by n square. This capital N is the amount of 5-ohm flux near the black hole. So as you keep on emitting dual giant gravitons, this factor decreases, and that's why the entropy of the black hole decreases if you keep on emitting more and more dual giant gravitons.
Yeah. So the end point of the instability, it's still a black hole, but now with a gas of gravity, gravitons, or giant gravitons.
Not gas, it's just one or
Just one.
Yeah, just one.
And the remaining black hole is stable, you say?
Yes, because I went to I went to a black hole. So if you want to find stable configuration at this point, you go to a black hole which is on the red curve, which is mu equals to 1, and this black hole is stable against emission of stable electrons.
Questions? Okay, it's 19.